Okay, Laura, are you ready?
Yes, we are.
Okay, thank you, Laura. Hey, welcome everyone. This is the 10th IEEE CEDA CAT for Assurance virtual panel. And the topic, as you can see, is a very, very exciting, very timely topic. How can we build trustworthy cloud systems and run a variety of cloud applications securely? Okay, so this is 11:02 this timing is not correct, 11:02 Eastern Time. I'm Saurabh Vunia from Electrical and Computer Engineering Department at University of Florida. On behalf of IEEE CEDA and IEEE Hardware Security and Trust Technical Committee, that's HSTTC, it's my pleasure to welcome you to this 10th CAT for Assurance virtual panel. I would like to quickly talk about this CAT for Assurance initiative, and then I will hand over to the moderators. The CAT for Assurance initiative started in 2020 October during the peak of pandemic. And this was done by members of the broad hardware security community. And we decided together to have a platform for rapid academic dissemination of open source tools and benchmarks, basically the research artifacts which are created by the community through a website. And that's when we created the catforassurance.org website. This website has received contributions from number of, I would say large number of hardware security researchers, about 80 contributors now, with more than 56. It's 56 was probably dated. Cat for Assurance tools and over 3,000 benchmarks. The website has received 60,000 users from 155 countries. So it's really a global effort, as you can see, and over 60,000 page views. We had so far 17 tool demos, 9 virtual panels, and thousands of attendees. So we are really proud of this effort, but we would like to invite you to help with this effort if you can. And the way you can engage with this initiative or with these people who are involved with the CAT for Assurance initiative is to share your open source tools, benchmarks, which are coming out of your research activities, upload the tools and benchmarks in the website, give webinars about your tools, and that has been very popular. And finally, if you would like to organize a panel or participate in the panel, that will be great. Gang Q, Sung Hyo, and Yejin are the co-organizers of this particular event. And they have, of course, actively supported these events throughout the years. They belong to IEEE, HSTTC, and CEDA organization. I think you probably have heard about those very well. And then we have also some technical sponsors, which is Warren Williams Institute from University of Florida, Mercury Systems, Northrop Grumman, and HII. Just to let you know that we have archived all these tool webinars and the virtual panels in the IEEE CEDA website. So if you go to CEDA and if you have probably missed some of the events, you'll be able to find the video recordings there and browse them. So I will encourage you all to do that. With that, let's talk about today's panel. I'm really excited to have this panel on such a great topic. And we have two outstanding moderators, and I would say a set of panelists who are truly distinguished, and the panel on this topic cannot be better in terms of the composition than this. So Mengmei Ye from IBM Research and Ramaya Mosti from Ampere are going to moderate this panel. Very prominent researchers and contributors in the field of cloud infrastructure and cloud security. Mengmei Ye is a staff research scientist at IBM TG Research Center working on confidential computing and cloud infrastructure. Received her PhD in electrical and computer engineering from Rutgers University in 2021. Her research work has been recognized with a distinguished paper with Artifacts Award at CSAC 2023, a Best Paper Award in IEEE ICCD 2016, and a Best Paper nomination at IEEE Host 2018. Ramya Musti is a senior principal engineer at Ampere Computing. She works on a broad spectrum of security features for next generation cloud systems. She received her PhD in computer science from ETH Zurich in 2015. And she has over a decade of experience in architecture, design, and validation of system on chips. Her broad interests include application of trusted computing principles to emerging disaggregated and heterogeneous cloud platforms. The panelists are Mona Viz from Intel Labs, Min Shao from Siemens EDA, Nathaniel McCallum from AMD, Xiaofeng Wang from Indian University, Mohit Tiwari from University of Texas, Austin. Really pleased to have all of them here in the panel. And thank you for joining. And it's my pleasure to hand over the panel to the moderators, Mengmei and Ramya. Thank you.
Thank you so much, Swarab. Really appreciate that. Hello, everybody. This is Mei from IBM Research. This is really my great privilege to be here, moderate the panel with Ramya together. So without further ado, I think let's start the panel today. And first, thank you so much for all of the panelists today for joining us, the very exciting topic about the cloud security. So let's first have a round of introduction from all of the panelists. First, Mona, could you please start with the introduction? Thank you so much.
There you go. Hey, well, thanks for the invite. Yeah, so I'm Mona Vij. I lead cloud security research in Intel Labs, and I've been working in security and privacy research for, I don't know, 25 plus years, for a long time, with a lot of focus on systems research. I think of myself as systems researcher, but I've been working in this area we call confidential computing, and we'll talk about that quite a bit in this panel. For since its inception, it was, I would say, the term was coined by Intel's inception of SGX, and I'm also part of the SGX architecture team. And since then, since Intel put SGX out there, I worked a lot with a lot of academic partners to advance the state of art of SGX, not only on the software side with respect to side channels and such. And over the years, we have built quite a few software tools and open source projects. And the one I want to highlight is Grameen Library OS that basically attempted to solve the SGX usability problems. Why SGX provided such a strong security solution? It was people found it hard to use. And Grameen allows you to run unmodified Linux applications. And actually, it's deployed in production today in quite a few use cases. And maybe we'll chat about that a little bit more as the panel goes through. But many of you will also hear this trend of what we're calling confidential virtual machines is appearing. So that's where my research is now. Me and my team actually have a small, very good team of strong researchers. We are all focused on this area, looking at what CVMs can do. And while these confidential virtual machines, they basically have a really large TCB. So there are challenges around can we really trust them? How do we do this workload identity or the attestation? There are challenges around that. So we are now taking this Grameen project and going after this lightweight trusted execution environments to be able to offer these security guarantees with these VM solutions as well. So I think I saw this quote from somewhere. VMs aren't heavy, OSs are. So whatever you put in a virtual machine it can be lightweight or heavyweight. So that's sort of the lightweight TDs is the one area of research we are focusing on. Really getting this fine grain attestation is the other area. And I cannot end my intro without talking about everyone's working in the AI space. And yes, we are working in this area called confidential AI, because that's sort of the driving use case. And looking at how confidential computing can help the deployment of AI. But we come at it more from systems side, so not just CPUs. Now the confidential computing is also moving to GPUs or other accelerators, and there is this work around extending trust to accelerators via this technology. Intel, we call it, I guess, TTX is TDX Connect, but it's standards-based approach. So there are industry standards like TDISP and ITE, and we really have to have a standards-based approach, because if you build these accelerators and no one can understand, then it'll be very hard to enable. And that's where the whole industry is moving. That's the other space we're working on, potentially looking formal verification of some of these protocols for both scale up and scale out. And last but not the least, I also lead an academic center called Trustworthy Data Center of the Future. At Intel, we fund researchers, and this was a center that was just kicked off earlier this year. Actually, Xiaofeng is part of that center. where we are looking at how confidential computing can be applied in a disaggregated and heterogeneous and distributed data center. And we have some really exciting work coming from several different top universities, and I expect to see that sort of impact the confidential computing space. And I guess that's it. Yeah.
Wow, thank you so much, Mona. I have to say, when I did my PhD, I worked on the confidential computing. I really read a lot of your papers and used a lot of your open source tools, etc. It was very inspiring, and also for me, it's a very, like I would say, great learning process for me when I was in PhD years, everything. And
Thank
yeah, thank you
you.
so much for introduction, and thank you
Yeah,
so much
thank
for
you.
being here. So we move to the next panelist, Ming from Siemens EDA. Ming.
Yeah, hi. My
Hello.
name is Min Cao. I got my PhD from Carnegie Mellon University in computer engineering. Then I have been working in the EDA industry for the last close to 25 years, last count already. I've been through Cadence and then worked for KLA later, and then joined Mentor Graphics. Right now, it becomes Siemens EDA. So long history with the EDA world, and then focus on all different kind of aspects of the front end design tools and the back end design, back end verification tools, working on all of those. Related to today's topic, so recently we see a lot of our EDA customers start to running EDA tools in the cloud, right? So then the cloud is a very different computing environment. So I have been spending the last 10 years trying to understand all different kind of computing environment to run the EDA tools. What's the requirement? What's relatively all the different things that you need to run the EDA tools effectively and comply to all the security requirements. Traditionally EDA tools is inside a air-gapped environment, basically, right? So you are inside your own firewall, and then all the security is handled across on the firewall layer. Then the EDA tool itself doesn't really need to handle that much. Now that the story changes when you are moving into the cloud, because it's essentially a shared environment, and you have the security measurement implemented on multiple different layers. How do you leverage that, and how do you utilize those different layers to actually meet the security standards for this environment? And how do you protect the customer's data, the user's data, in terms of security? Because and the security can have different aspects, right? So if you work for a government agency, you need to comply to a policy. And if you work for a private sector, for other companies, they have their IP protection requirements. All this comes into play, and then there's make everything very complex. And also the other aspect is EDA tool usually, especially the area I work on right now, the backend tools, they usually consider to be high performance computing tools. So this high performance computing tools requires performance. Now, when you implement a security measure, and then the security measure and inevitably introduce overhead. So how do you understand that overhead? How do you mitigate that overhead inside your software stack? And then so you can maintain the performance. You use the right the security measures at the right place. So then you meet the standards, and then you still don't sacrifice that much of your performance. So that's those are the things that I myself has been lately just doing some work with with IBM, and so for the confidential computing, and especially in the container world, because container is a different way of doing virtualization. So those are the things I'm focusing on. So again, I'm very glad to be here. Looking forward to have a very good discussion with everyone. Thanks.
Thank you so much, May. Thank you. That was very interesting. I don't know if the audience, everybody, has some background about EDA workloads. I don't know. Maybe Ming, maybe you can elaborate later on in the further discussion. Because in my opinion, EDA with as a service, and also with cloud security, all of the important things we have to address, etc. It's a really important area to explore on, to really say how we really offload EDA workloads to the cloud, how we maintain security and maintain the performance, exactly as you just briefly mentioned. And I'm really looking forward to the further discussion you're going to share with everybody here. Thank you so much for being here. Thank you. So our next panelist is Nathaniel from AMD.
Hello, everyone. Thank you for having me on the panel today. Glad to be here. My name is Nathaniel. I am a technical fellow at AMD, where I lead the orchestration and confidential computing team, where basically we handle everything that goes from the kernel upwards. So all of the user space tooling, all the integration into orchestration, et cetera. My background, I was at Red Hat for 10 years, where I did cryptographic research. I am the inventor of one of the inventors of the McCollum Reality Key Exchange, as well as I probably have the claim to being the first independent implementer of both Intel SGX and AMD SEV. I've been working in the confidential computing space now for probably 7 or 8 years at this point. So thrilled to be here. Thanks for having me.
Great. Thank you so much, Nathaniel. Really appreciate that. And thanks so much for being here. I saw a lot of, presentation you had or discussion online, and also a lot of like conferences or forums. And thank you so much for being here. Thank you. So our next panelist, Mohit from UT Austin.
Thank you, Mengmei. It's great to be here. I am at UT Austin and at Symmetry Systems, taking some of the work from UT Austin and trying to commercialize it. A lot of the core of my work has been around information flow control, which is really just put simply, we all care about data types, things that assets that we care about. We worry about sharing it with different types of identities. And the whole question is what types of data are flowing to what types of identities. It's just super simple. So I could say like, hey, my personal photos only go to people I want to share it with. But what we have been doing really is I started off looking at it at a hardware level, but more recently, we've looked at large scale sort of service mesh type of deployments, how we have distributed workloads now deployed on the cloud. So that's been one line of work. And then the parallel line of work has been these workloads really run on not just CPUs, but also accelerators. And how can we now take lessons from all the fine-grained information flow control that we have learned that are really hard to retrofit into CPUs, but we could kind of build a system stack that makes accelerators be more secure than potentially some of the challenges we have had with CPUs. So this has been the two directions. And one thing I can quickly pop up to share is as part of going out and deploying this information flow control at big organization scale, I got to see what these organizations look like. So maybe just taking a quick gander at here is a large organization and an information flow graph in that organization. And really what this is showing is everything blue is data. So we care about data types. Every other color is users, services, roles, groups, etc. And this is the permissions flow graph or the operations flow graph across the environment. And you can see that it's a crazy mosh pit. This is what we are trying to protect or trying to layer policies on top of. But in practice, there are many organizations who do a really great job, and you can see they can build really segmented environments with data flows that are, all the edges are data flows, the data flows that are much more controlled. So there is a path from, most likely finding places that look like what you see on the left, but then moving towards the right. And now once you layer on workloads and data types flowing through it, how can we give guarantees all the way down to the level of bits and gates when we run it on accelerators? This is the overall theme, right? This distributed workloads, whether it is AI on an accelerator or on general at the enterprise level. This is what we work on. Very happy to be here. Thanks for inviting me.
Oh, thanks so much, Mohit. Thanks so much for the exciting project they've been working on. And being into a lot of presentation and read papers, I really learned a lot from your project. Thanks so much for being here.
Thank you.
Thank you. So our next panelist, Xiaofeng from Indiana University.
Yeah, thank you for inviting me. And I could be, I could be the second panelist who are going to show some slides, and I'm going to show 7 slides. And I'm a professor from Indiana University, and I'm a security researcher. So I've been working on system security for more than 20 years, right? And also I'm the director for NSF Center for Distributed Confidential Computing. So, and I'm taking advantage of this opportunity to introduce our center. And 1 second. Okay, can you see the slides?
Yes.
Okay, So in the center, the NSF Center for Distributed Confidential Computing is one of the largest investment the National Science Foundation in the United States has ever made in the area of confidential computing. I'm honored to be the director of the center. And so here I'm gonna briefly introduce the background story of this center. So as you know, the advance of AI and data science and the application in critical domains such as autonomous driving, banking, and healthcare all depend on availability of large amount of data. And but this advance could be stifled by the barriers to data sharing due to privacy concern. Among all the challenges in data protection, the most difficult one I'm going to say is how to protect data in use. As you could imagine today, if you are training a large language model on public cloud, for example, over electronic health record, right? And you have to decrypt the data, even the original record has been encrypted, and to make sure the computing can accomplish within reasonable amount of time. But during this process, the data, content of data could be disclosed. So a ground challenger for data protection has always been how can we make sure that the content data can only be disclosed to the authorized party, and when we're using it, and how can we do this in a practical and scalable way? You know, and I'm going to say the practical and scalable solution to this holy grail of data protection will change the computing as we know it, enable a whole set of capability we don't have today, such as trusted service, confidential outsourcing, and confidential collaboration. If we had this capability, no longer do we need to worry about data gathered from us, from our car, because we will have the confidence that the content of data can only be utilized to help us drive more safely and more effectively. And the hospital could utilize the cheap cloud computing resource to analyze patients' electronic health record to reduce healthcare costs without concern that the content of data will be disclosed to the untrusted party. And the bank can work together, utilizing machine learning models such as graph neural network to analyze the money trace across the bank for anti-money laundering without concern they may have to disclose their customer transaction to their competitor. But the problem here is the technology foundation for this breakthrough are still not mature yet. With crypto solutions such as homomorphic encryption, secure multi-party computing, still orders of magnitude behind. The only practical alternative we have today is hardware-supported trust execution environment. Those hardware TE, they are designed for isolating computing from its untrusted environments. But the problem here is isolation alone cannot help us achieve practical data use protection. Why? Because there are several important questions have not been answered yet. For example, how do we know the program running inside the T itself is trustworthy, right? And how do we know during the run times each computing node running the right program enforcing the right policy? Right? And how do we know the whole workflow, which involves CPU, GPU, TE, and they are policy compliant? And the last but not least, how can we effectively communicate to the human user to convince them of the utility of this technology and also helping them to utilize those technology effectively? So the mission for the NSF Center for Distributed Confidential Computing is to lay down the technology foundation for this breakthrough, and on top of it, to support transformative application. Our vision is to create a research, education, workforce development environment to enable scalable, practical, verifiable, and usable data use protection on today and tomorrow's cloud edge system to help maintain US leadership in AI and data science. Yeah, for this purpose, we have 9 PIs from 8 universities with expertise cover a wide spectrum of related area. We are working closely with industry partners, including confidential cloud service provider, T middleware developer, and the T manufacturer, including Mona, Intel, and also including geologists and the folks from AMD. And we are also working closely with healthcare practitioner and IoT and autonomous driving experts. So here's what we are doing now. We are building the foundation for distributed confidential computing. On top of it, we are supporting transformative application. And from those applications, from what we learn from those transformative applications, we will further improve the foundation. And the foundation will have these 4 building blocks, right? The first, assurance of code. We are developing an open ecosystem for vetting and certified program to be run inside T to make sure they have the capability to enforce data use policy in open, transparent way. And also, we are developing a policy language to allow the data user to specify their policy and a mechanism to enforce this policy during elastic computing. And also, we are working on side channel to developing technology to suppress side channel leak, and also to prove the policy compliance of the whole workflow to the end user. And also, we are performing user study to understand the public perception of those TE technology and the risk communication mechanism together with user interface to help stakeholder to more effectively utilize those technology. For more information, you're welcome to take a look at our website. Thank you.
Thank you so much, Xiaofeng. Thanks so much for being here. This is very exciting organization altogether. Thank you. So for the audience, as you can see that today, it's great that we have really panelists from both industry, academia, working on all of the different domains, including application level, system architecture, even hardware level. So if you have any questions, please feel free to post in the Q&A section in the Zoom feature there, so that we can really get the discussions, answers, and from the panelists. And thank you very much. Thank you, panelists, for giving a great introduction here. While we are waiting the Q&A session, the Q&A questions from the audience. Ramya, would you like to lead the discussion and start with a few questions first?
Yeah, thank you very much.
Thank you.
Hi, I'm Ramya Masti. I'm a security researcher and architect over at Ampere Computing. And I'm happy to be here today. Very grateful to be part of this event. And thanks to all the panelists for taking the time to talk to us today. I'm sure it'll be a fantastic conversation. So to begin, maybe I'll start with Min-Sao. Could you say a little bit more about what specific concerns you have in terms of EDA applications moving to the cloud, and how trusted execution environments can mitigate or help address some of those concerns?
Yeah, sure. I'll start with the several statements, right? So let me share one page that I prepared to help myself to explain this. So if you look at the EDA software, right? Let's see. Okay. Okay, if you look at the EDA software, I call it EDA software in the for the security solution. This is both the provider and the consumer. So why is a provider? Provider, because EDA software is used to design all the design and manufacture all the hardware that is used in the computing environment. So that means EDA software need to implement all the algorithms and the methodology that's required during the hardware designing phase. So that is the providing side. Now if you look at EDA software, eventually you want to run inside the cloud. So this is once you're inside the cloud, you are facing a long stack of things, right? So at the bottom layer there's hardware, and then there's virtualization technology, which is virtual machine, and also I consider container as a virtualization technology. That's put one layer on top of the hardware that you can actually implement, the runtime environment for that. Now, above that, there are software components. So nowadays, EDA software is not a single machine software anymore. It's a vast distributed processing software, right? For example, the product I'm working on is the EDA from the Siemens EDA is Calibre. Calibre usually runs on hundreds of machines that as one single job. So that's all the when these are distributed, each components runs on different hardware and run on different virtualized environment. There will be a communication layer. So just tag along with what Xiaofeng actually commented earlier. What is the security requirement when the communication happens? Right. So like I said earlier, so when you actually have this kind of communication, inevitably you will have some overhead because there's encryption and decryption involved. What level you want to use that? So that's between the software components. Then above that layer is the software system itself. Let's still take Cadbury as an example. Cadbury input is a SBIF. Traditionally, a lot of the foundry providers require the SBIF to be encrypted. So you need to read the data in to be encrypted. And also it works on the layout. The layout usually contains IP blocks from all different vendors. You want the layout to be encrypted. So this data ingestion and then also the data production also need to comply with the security measure, use the security, all the security solutions that's implemented from the software library level and from all different levels that below here. And then the next layer will be the user access, because when you're inside the cloud, you're thinking about putting this as some kind of service, right? So it's unlike the traditional EDA environment. So the user buy the software and then just install it in their data center. They control the access on their own. But now you are having a sort of like a public-facing portal that people can access the software. So then the security the requirement need to be implemented on that layer. So, that's what where I'm saying where the challenge is. There are security solutions implemented on each one of these layers. On the hardware layer, there are features on hardware that enhance the security for multi-tenancy on the hardware. On the virtualization layer, there are also security solutions and so on. And for the EDA software, is pick and choose which you can rely on, right? So, it's too naive to think, okay, we get just get a free ride. It's security is everywhere. We just write our software in the good old way. It's not really that simple, right? So you need to look into this. And the other thing like I commented earlier is how do you understand the performance impact of all these solutions? Choose the right one to actually meet the security standards and also that don't impact your software performance. So that's my opinion about these challenges that's facing from the EDA software when they come to the cloud environment. The challenges coming from the security aspect.
Okay, thank you. So, Mona, I know you were talking about different types of trusted execution environments that can enable both applications and virtual machines or entire OSs to run securely. Could you perhaps say a little bit more about how they help secure applications like the ones that Minsao was talking about?
Sure. Yeah, so first of all, yeah, good that Minsao showed that stack, right? The whole stack, and this is how the traditional system security is built. Today, we build secure systems from bottoms up, right? We trust the hardware, then we trust the firmware and the VMM and the OS on top, and then we traditionally have had this whole trust TXT and secure boot where you can actually put some trust in your software in your environment, but it's still a really large body of code. And when you start putting sensitive data like EDA tools which have sensitive IP, and then the other area where several of us are working, and actually this is a lot of the work we are also doing with Mohit's team on whole AI side of things. When you take some of those things to the cloud, this we need higher security guarantees. The current way of doing things doesn't really work. And the other thing is not only you're putting trust in this large body of software, you're also putting trust in the cloud admins. And we have also seen this issue of insider attacks. So historically, and I was not even sure how much of EDA tools are already running in the cloud because my assumption was a lot of it runs on on-prem data centers. So when you move it to the cloud, you are trusting the cloud admins as well as this large body of code. So this is where I think Xiaofeng sort of introduced confidential computing, but just so that everybody is clear, and maybe some in the audience don't know what confidential computing is. It's basically, this is a new technology which protects data in use by performing computation in a trusted execution environment that is rooted in the hardware. It gives you these isolation guarantees from privileged software and admins by mapping your workload or the application to a secure area in processor and memory, which is protected from rest of the environment. So even if you are a VMM or a super user or the cloud admin, you can't really, not only you can't really see, so confidentiality, but it also sort of provides you integrity guarantee that no one else can modify. And then you can actually verify that via a process called attestation. So you don't really have to trust the cloud provider. You can actually verify that you are running exactly the code that you wanted. So as I mentioned, when this field of confidential computing started, it started with SGX, which was basically process-based isolation. And it was really nice because it gives you this small TCP. You're only putting your application in an enclave. You don't even have to trust the operating system or the VMM, just the hardware and your enclave. But now when we start moving complex AI system or EDA tools, which are, like Min said, they're distributed systems, moving that system into into SGX can prove to be really, really difficult. So we have some tools, like I mentioned, Ramin, you can run these unmodified systems, but how do you build this complex distributed system? So the industry has now, to solve that ease of use problem, we have these virtual machine based enclaves. But now you brought this big operating system into your TCP, but still you have virtual machine out of your TCP. So you don't have to trust the cloud admin, and you don't have to trust the virtual machine monitor. So the security guarantees are slightly different, but now you can run these host of containers. You can run the containers with SGX or with TDX, but it's just, I would say the deployment is a little bit easier. But then you do, your bar is slightly lowered in my mind, because you are running this large body of code. There is no good way to attest to exactly what you're running. We are somewhat back to this historical TXT secure boot attestation problem. And that's why I mentioned we need to, but we can address that problem. There's industry, so many of us in the industry are working on solving that issue. But I would see, depending on the use cases, I would say both VM-based enclaves and process-based enclave will continue to live. And I'm also proud to say, while the whole industry, all the hardware vendors, AMD, ARM, and all of them are offering CVMs, Intel is uniquely positioned to offer both process-based and the VM-based.
I think that's a great summary actually for the audience, for people who are not familiar with CVM versus SGX, like process CEs. So thanks. So you raised an interesting question, which is essentially one of deployment, right? Like widespread usages of security technologies tends to take time. And so my next question is sort of for Nathaniel, given his background. So in your experience, what are some of the big challenges in terms of actually getting TEs to get adopted, right? So yeah. And
Sure.
yeah, go ahead.
I think the biggest question is, are we actually solving problems that people need solutions to? We can create a bunch of new technologies, but the question is, what are we actually building? And the way that I look at this is that I take a first principles approach. So the fundamental problem that we are trying to solve is that we have some sort of a secret, whether that's some sort of data, or whether that's keys. And when we disclose that to some remote party, we want to have assurances about how that is actually going to be used. And the really tough thing that we have is that this is actually the intersection of two distinct problems. The first problem is a problem of privacy, which is, how do we ensure that nobody is observing or tampering with the operation? And the second problem is a problem of supply chain, which is, how can I know precisely what the operation that I'm doing, what is it actually composed of? And so I think that the solution to solving these deployability problems is, one option is we can create a really small TCB, but the reason we have larger TCBs is because larger TCBs are actually useful and provide us a bunch of functionality. And so I'm actually focused on decomposing this problem in a different way, which is, what we actually want to do is we want to have something like a confidential VM, And we want to be able to break that down into a set of meaningful chunks of operation, where each operation is reasonably scoped, and where we can have strong guarantees about the visibility of the data within each component. And then each component can be identified through some sort of identification, right? Typically, this is something like an X509 certificate, but some kind of workload identity. And so this allows us to transition, I think, from a world where we disclose secrets and data to, some sort of identifier where the identifier really identifies the party that is running an application, but gives us no indication of what the actual privacy primitives of that are or what the code is actually going to do. So we have very little scoping on the data that we're disclosing. And we want to move to a world where we can use all of our existing security primitives, plus these new confidential technologies to create a highly composable world where we can identify each of the components whenever we release this data. The data disclosure is scoped to a specific algorithm running at a specific time within a specific context and for a specific duration. And so this allows us to capture all of the invariants that we are normally used to assuming. We tend to make lots of leaps of faith in this process, and I want to be able to remove these leaps of faith and be able to quantify them. So we should know exactly where the leaps of faith are, exactly who we're putting our trust in, for how long, and so forth. I think that that's the fundamental issue we're trying to solve as the industry, and we're all putting together tools to be able to make that world come into a reality. But I think it's really essential for us to understand what it is, what's the big picture that we are trying to solve, and how do we actually get to that destination.
Yeah, that's great. So in a way, I think there are several layers to this problem, right? There's the problem of establishing trust, and then there's the problem of trying to track what is running in a trusted execution environment. And it sounds like, there's plenty of work to do in terms of actually trying to make sense of the information that everybody's getting out of the attestation process of a trusted execution.
Yeah, I have a job for a few years at least.
Yeah, I mean, job security, it's not a bad thing. So yeah, that brings me, like, as we talk about layers, right? That sort of brings me to Mohit. So in terms of actually establishing, or you were talking about information flow control, which almost seems like yet another layer over and top of a trusted execution environment, right? Like, you want to make sense of how data is flowing both at a micro and a macro granularity. So can you talk a little bit about what the challenges are with environments where perhaps you don't have the privilege to be tracking it, or an untrusted entity is more privileged in terms of being able to interfere with information flow control?
Actually, that's a really interesting question. I'm not sure I fully understand it. So I'll try to just interpret this at least as like, okay, step by step, like what's the challenges that you could have if you have to set up a multi-layered information flow control? I think that's one. And I think Min's slide here was really helpful because he kind of laid out the different layers. Like we need, if you start from the bottom, right, the two enclave styles that Mona mentioned, but also other just confinement mechanisms, you want to be able to show that these are indeed leak-free, right? So SGX was not designed for side channels. Threat models changed going forward, and now you have to account for side channels. So step 0 in terms of challenges, what I would like to propose is to really work on, can we build primitives that we can update the threat models for as new threat models emerge over time, right? The kind of first versions of things that we have designed, we kind of defined the notion of a threat model, right? Like in one case, the process-based threat model, the SGX, we have, we don't want to trust the bulk of the app. We don't want to trust the OS. We don't want to trust the VM. I think that's really awesome, because really who we are not trusting is most of the developers, most of the app components. We don't want to trust the VMM and the cloud providers, right? So I think being able to update these policies where like, hey, I actually am okay with physical security, I just really care most about software security against the OS versus software security against other application layer components versus, I think we talked about privileged administrator. One really interesting nugget that I learned from just kind of deploying these things in the practice is really big companies. You would imagine that the admins are the highest ranking, most context aware people in the company. And in practice, running the cloud is actually often offloaded to services companies who are the least privileged people in the company, who now by definition have admin access into the bulk of that cloud. If you remember that crazy picture of the jellyfish that I showed, people who have admin access into the bulk of that cloud are just folks, they might be in untrusted, less trusted, let's say, countries / organizations than your own, right? So being able to define an enclave for, or define just confinement primitives that you can update the threat model as you go along. I think that's probably the biggest open question, one big open question in my mind. And then I think Mona referred to this before, is the software stack. It's no use having a really good primitive at the bottom unless we can enable developers to really use it, where developers are really focused on their core use cases, not trying to imagine all the threat models and kind of build out things. So building out frameworks, that's really helpful, where we can tie an end-to-end guarantee. This was a question in the Q&A, right? Like, who are the two ends? Is the end user who is uploading their private data and asking for some confidential inference to be run? Or is the end the two software components who have taken on the responsibility on behalf of the users? But it's kind of like in a service mesh framework, the software companies / products are now negotiating on behalf, kind of in bulk, and setting up clean rooms for. So I think this definition of who is the end-to-end and then building like a framework for that. These are the kind of, I would say, like two blocks, if we can make progress on, would make a pretty solid dent. There's no reason why we should be staying with the current model where we trust everyone, like all the software providers, all the 200 software providers that they embed into their software and all the cloud. I think, pushing a lot of energy into confidential AI, this makes a lot of sense if we can get these two widgets right.
Yeah, I think there's a lot of opportunity there, and I think there's a lot of progress that we can make as a community by taking a first principles approach, right? Which actually brings me back to one of the questions we had from the audience, which I'll perhaps start with Xiaofeng.
Mm-hmm.
So, like, since you're working, like, you're looking at heterogeneous distributed
Mm-hmm.
cloud systems. Can you say a little bit about what is the challenge in establishing trust, for example, say on one machine versus such a distributed cloud, right, which has so many heterogeneous components, like establishing trust in just one computer system, like just a CPU versus a CPU plus a GPU plus a NIC.
Yeah.
Like, what are some of the things that come to your mind in terms of the big problems that we have to solve?
Yeah, there are a lot of challenges, and even you're talking about you want to establish trust with a CPU T or GPU T itself is non-trivial, because so far the model just like I'm sorry to say we need to trust in just Intel, because Intel certified programs for us, right, and AMD certified program for us. But in the open world, as you couldn't imagine, people will develop their own program, right? And how do we know that the program will faithfully enforce a user's data use policy and will not leak out your private information, for example, electronic house record, to someone else? And so how can we make sure, and who is going to certify this program? You cannot count on any user to analyze the program, right? So that's the reason we build up these open ecosystems, and we use TE. We use TE itself and to certify the program. We have blockchain to just record the process. So the process is open, transparent, people can verify it. And when it comes to distributed environment, it becomes even more complicated, because you want to make sure on two different T, CPU T and GPU T, they are all running the trusted program. And the information couldn't leak out from your CPU and GPU, right? And attestation, what have been done, the remote attestation, and you're showing to the user what running inside the TE, and together with what we are doing the certification, right? And you not only what running inside the program, but also understand the semantic and the program will not decode information at all, right? But perform this attestation across different parties and different hardware construction could become even harder. And even more challenging, talking about the topology, infrastructure. Even if individual TE node are not decode information, but the whole topology could decode information, and which you have no idea about. For example, if you have a distributed AI-based and healthcare system, which deployed on the cloud, right? And you have a TE module which analyze the patient's test result. Then based on test result, it will further communicate with diabetes analyze module or heart disease just the analyze module, right? But and even if you couldn't see whatever happened inside individual TE, but the mere fact that the test module has communicated with the diabetes modules could indicate that the patient may have a diabetes problem, right? So how can you cover the whole information to ensure that not only individual TE node, but the whole workflow will be policy compliant, become even more challenging. And also all these things need to be done in a way that we are gonna we are gonna and support real world application and make sure that have minimal impact on performance, particularly in the machine learning age. And we are talking about large language model. We are talking about people wants to get response within the very short period of times, and become very hard. And another barrier has become technique itself. Even we have the best technology in hand, still people don't trust us. And there's policies, and we need to spend time to communicate with top policy makers to change their mentality. And for example, although NIH has increasingly allowed people to ship the encrypted data to the public cloud as long as it's reasonably protected. But and for hospital, for example, and no matter what you are doing, right, and you couldn't, even for the encrypted data, you couldn't move it to the cloud. And so in this case, even the technology can provide a reasonable secure even for the hospital, but their policy does not allow them to send even encrypted electronic health record to the cloud. So how are we going to communicate with them and to demonstrate what the security guarantee we can provide? And I think this is very critical, and both for the hospital and more importantly for policymaker, because many organizations, what they care most is compliance.
Yeah. I think you nailed it there. Like, there is a layer beyond the technology that needs to come together in order to make these solutions more widespread. And one among them is actually compliance to various either standards or various regulatory requirements for different industries, whether it's fintech, healthcare. And we as a community, I think we have to work towards convincing them that the guarantees that these solutions will provide is actually good enough for the applications or the requirements that they have, right? Yeah, which brings me to the audience question. And this question's for Nathaniel. So I think we talked a little bit about supply chain and identifying components of software stacks in order to get assurances or make sense of what exactly an execution environment is composed of. Now, do you think that's something that we could extend into the hardware? Like, you have a platform with many components that are integrated, like even just a motherboard with a CPU and perhaps some peripherals. And what are the challenges, for example, in terms of figuring out this composition problem for software versus hardware?
Yeah, I don't fundamentally see a difference here. The composability problem exists for software and it exists for hardware. It's all roughly the same problem. The details of how you deal with hardware versus software differ, of course, but the key principle is that when you're composing a system, all of the individual components need to be measured and identified, and that you need to have some policy that you can use to make decisions about the trustworthiness of a set of components. In terms of hardware, there's a variety of things that are coming up in the industry right now. Of course, as Mona talked about, TDISP is a thing. All of the chip manufacturers are going to be shipping support for that. We're going to see devices hitting the market shortly. That is certainly part of that problem. And a big part of what TDISP does is it allows you to create a confidential VM and then be able to attach devices that can be attested and then trusted. So that kind of goes to that problem as well. However, just looking out, and there's no proprietary information here. This is just me kind of speculating about the future. Looking forward as to what companies are actually doing, there's a whole lot more componentization happening even within devices. And so, you can see that, for example, even just with AMD's, chip layout, the way we're using CCDs, chiplets are a thing that's coming to the market. And so we're actually going to see more disaggregation, more decomposition of the hardware chain. Each one of those components, particularly where it has a discrete supply chain, is going to need to be measured and identified. And so this is why it's super important for us to be able to build highly dynamic, composable policy systems on the top of this, because we need to have the ability to move the individual pieces in and out. I think the way most people sort of conceptualize this problem today is that they sort of think of like, I'm going to pick one hardware platform on maybe one cloud, and then I'm going to run one virtual machine. And then I'm going to basically set this whole thing up. I'm going to run it once and get a measurement of the whole system. And I'll have this big monolithic thing, which I'll validate, right? And that's certainly a reasonable goal for the near term. But I'm looking much further beyond that to a place where we can actually dynamically compose each of the components in the system, dynamically evaluate each of the components in the system, so that we can have a far more dynamic policy evaluation on the other side. And what I want to get to is a very high level descriptive language. I kind of imagine in my head that we write policies in something that's human readable, where we would say, like, I trust firmware releases for AMD for this CPU, so long as it doesn't have any active vulnerabilities. And then we have some tooling that's like a policy compiler that goes out and takes that human language along with human language about all the other layers, and then can reach out to all the data sources. These are things like maybe transparency logs, publishing information about firmware and so forth. And this compiler grabs, all of these data sources and turns this human readable policy into something that has no ambiguity and is machine executable. This allows us to have institution neutral verifiers, for example. So there's a lot to be done in this space. I know I've probably used way too much time answering the question, but fundamentally, I don't see these as discrete problems. The problem of hardware supply chain and software supply chain are very closely related problems, and we need similar primitives to be able to deal with them at all the different levels.
Yeah, that's great. Actually, the pointer or the reminder that even single packages can be disaggregated and sort of distributed systems within a package, I think, yeah, it's a fantastic observation. And there is some really interesting work and very challenging work that can come out of just looking into problems in that domain. I just want to take a moment to remind the audience to post questions into the Q&A using the Q&A feature. It makes it easier for us to track it. Yeah, I might not be watching the chat very closely. Yeah, because I'm looking at my screen otherwise. So circling back, right, like we've talked a lot about attestation and supply chain and figuring out components that are running in an environment. But it's also true that we tend to use hardware from hardware providers, and not everything tends to be transparent, right? Like there's a line to draw between, like, what version of microcode am I running and what does it have versus, if I get a hash of piece of microcode, then what sense do I make of it? So if I can turn that question to Mona and say, like, what are some of the practical challenges you've seen with years and years of deployment of SGX, in which you had to convince people that a given measurement is good to validate, in the sense that, it's good enough that they validated the hash of a piece of code when they don't really know what the code is. So
Yeah, I guess that's the $1 million question. For one, first of all, I think that's the biggest problem. So we talked about this whole great feature Ts have around attestation, right? You can exactly know what you're running, but how do you establish those good known values, right? And historically, we can, some cases, you can actually either open source your software and then people can examine it or whatever, and that's good. But I think that, by the way, itself proved very challenging, right? Because software changes. I'm deploying a service today, some version, there's some other service. How do you now keep these good known values for these software? So some of the early deployments, while it was such a great feature, they walked away from it. We have this idea, we call it MR signer and MR enclave, meaning one is you can know exactly what code you're running, so you can verify the hash, and then other is you just verify that it is coming from XYZ services. So I trust this company to do the right thing. And a lot of people pivoted towards that. While it works, it gives you weaker security guarantees. And now what Nathaniel was saying, when you have this huge blob, you have the whole Linux operating system and some middleware, an application, am I going to publish one big value? And even if I publish 3, 4 values, those are constantly changing. So that's why this verification, while it's a great feature, I think in practicality, figuring out how we make sense out of those hashes is a huge problem. And by the way, so there's this data collection side and there's a verification side. So there is a lot of work happening on the side of the software supply chain, meaning you can make sure all the way from when your software was generated, compiled, and we maintain the hashes as it goes through the CI/CD pipelines, because you can introduce issues at any stage. And we are trying to, there's some work happening in open source community as well as my lab to get that. But then I still think you can collect all that metadata. It's when it comes to a verifier, either you are just going to trust the provider, in which case is MR is just signing enough, or are we raising the bar? And it's the same applies to, and then hardware side, it's even more tricky. So you at least in enclaves, I guess we are saying you still have to have some root of trust. So hardware is your root of trust. Intel publishes, when Intel says, yes, you're running in an enclave, or AMD says you're running in an enclave, you are trusting that the root of trust is protected. This issue that someone brought up, can there be malicious circuits and backdoors, and you are trusting them to make sure that they don't exist. There is, but I think as we go forward, maybe we can publish some of this supply chain data. I haven't seen anything. Software supply chain, we are seeing some movement. But I think this is just a hard problem. I actually think that's why we have so many of researchers working in this space, to the verification side. How do we establish those good known values, especially as we are building these really complex distributed systems? When we did the enclaves early on, right? You have one application or maybe one container, you talk to it directly, and you can verify it's exactly running and you prove it. But these days you go through an API gateway, you're not even talking to it directly, and then it's a mesh of services, and establishing trust in that needs this, I guess, layered approach. And I still think this establishing good known values is a tough one. And I think some work is happening on, instead of just the hashes, can I associate some policies to it, right? You don't have to just trust this hash. The hash, it can say, I am adhering to these policies, maybe some data use policies. And I think there is a shift towards that as well. And you attest to those policies rather than certain claims you can make. And yeah. So I would just say it's an active area of research, then and remains to be seen how it progresses. But in early days of SGX, people shied away from these hashes. They were just relying on MR enclave, and I don't know what different production systems are exactly doing in practice today.
I think for a long time with trusted computing itself, given that it typically gives you like launch time guarantees, like you know what you put in there to begin with, as well as given the fact that software typically evolves very quickly, more so than at least hardware used to. I think the challenge of maintaining a notion of what exactly is my system has always been challenging for trusted computing, even pre-SGX, right? Like just
Exactly.
attestation in the TPM world was a challenge. So yeah, I think that remains open even after multiple decades, pretty much at this point.
Exactly. So I think to me that it's the same problem whether it's a VM or a CVM. The only difference is you have hypervisor out of your trust boundary, but establishing trust in the code that is running inside the CVM, it's been a difficult problem to solve for last 20 years, right? And so that's why I strongly believe we are going to pivot towards these lightweight TDs, where you're not running this complete operating systems and many different applications in the CVM. You would be running a lightweight environment. You could run many of them just like enclaves, and then it's much. I mean, it's relatively easier to establish trust. It's not that problem of trusted boot and the large operating system, and something like Grameen TDX, which is few megabytes of code. You can raise the bar, and that's why I think this lightweight TDs or lightweight CVMs is the future if you really want to establish trust via attestation.
Yeah, that's great. I know that we have about 20 minutes before we wrap up. So what I thought we'd do is go around the panel, and I think I have primarily like two questions that I hope would actually create more collaboration or open up new research directions, both for the audience as well as for everybody to think about after this event. So maybe I'll begin with the academicians, right? So I'll begin with the professors. Like, what do you see as a challenge when you're working in this space in terms of not having access to things, or what do you think the best way or a few things that industry can do to help you address some of the research questions that you have in this space, right? What could they potentially give you access to, or what could they potentially talk about? So yeah, maybe we can begin with Mohit.
I was hoping you wouldn't call on me because because I was trying to sort my list and draw a line.
We can also go back and forth. Yeah, we can also
I'll give a
time.
quick answer, and I'll just back off. The kind of dumbest, simplest, most valuable answer is money is great. Just keep dropping money. We'll keep training grad students. That's awesome. The other kind of answer, I mean, actually, Mona mentioned this already. I've seen the Intel team at work for a few years, and they're just incredible at pulling together different types of teams, setting up centers, and giving really detailed feedback on what kind of constraints make sense for solutions to have. Because I could say like, hey, write your entire stack in Haskell and Rust and you're in good shape, but there are many shapes to the solutions that actually are more amenable to deployment versus not. So I think just this kind of fine-grained interaction is incredibly valuable. So thanks to Mona and the Intel team, but also I assume that this type of interaction is really helpful. And the second thing that I've found really valuable recently is a lot of data sets are just quote unquote too secret, too sensitive to be shared, but that's where a lot of the really hard open questions lie. Min brought this up, Shafeng brought this up, and when we were meeting with IBM, they brought this up as well, like just the cloud permissioning, like how is the cloud set up, right? And if you kind of look at the networking side of things, how is the networking? We're working with a Fortune 10 pharma company here at UT, and just how their organization is laid out is so sensitive because they don't even know what it is. They have grown over acquisitions over tens of years. but they also can't just release it, because now that tells attackers what are the main points of attack and so on. So this kind of counterpart of this problem exists at every layer of the stack, right? We don't know what the user policies are for doing Copilot security research. We don't have an enterprise organization where we can run adversarial attacks and test. All the way down at the hardware, if we are putting in microarchitectural things for performance, you can't directly tell us, but maybe just kind of having some abstract spec of, what interfaces. Like I've been, one of my favorite asks is, can we put microarchitectural data flow related tags or security domain related tags in the microarchitecture, right? But obviously this is a bad idea for many, many reasons, but just kind of knowing why it is, or maybe there's some abstract spec of the microarch that can be exported out that highlights more of these reasons. Because one of the classic constraints is like the end users will now learn more of the microarchitecture if the more of the microarchitecture behaviors and counters are exposed directly. And hence it's not exposed, but hence they also don't get used for good use cases for defenses. So I think, how do we unlock this lack of a data set? How do we get people access to more data sets in addition to more constraints, in addition to more funding? These are the 3 prioritized use cases.
Yeah, that sounds like a good list. Yeah, we're well prepared, I guess. So, Xiaofeng?
Yeah, just and I think for the research in confidential computing, right, we have to work closely with industry. We have no other options. We couldn't do the things by ourselves because and if we want to have our research have a real world impact, right? And it is we need to work with hardware manufacturer, particularly Intel, AMD, and also confidential cloud service provider. This is very important to us. This is because, and in the end, academia cannot drive the developer of this hardware-based security, and we don't build this hardware. And we can propose some design, we can propose whatever things. If people don't use it, right, it will only stay on the paper. Right? So, and I can tell you my own experience. And we, for this NSF Frontier Award, is one of the highest category of NSF award. We tried multiple times. The first time we were ambitious. We come up with a whole stack from software to hardware, from hardware to software, and then it didn't work out because later I realized, just in academia we cannot drive the hardware. We can come up with design, right? But if we want to make sure, if we want to, in the end, have the confidence and our research outcome will have broader impact, we need to make sure, indeed, people are going to use that hardware. We don't build the hardware. So, and the current CDCC centers will focus on the software stack. And we are trying to make the technology agnostic to different hardware component, right? And so no matter what kind of, you could use SEV, you could use PDX, SGX. On top of it, we can utilize our technology. So that's the whole idea. But in the meantime, when we executed the plan, we realized that if we leverage some unique feature of the hardware, we could have better results, right? So that's the reason, we were in conversation with Intel, with Mona actually, and I'm really grateful for Intel, which support us under this and the trusted data center for future. We're also part of the effort. And so I think this, and we learn a lot of things from the what Intel can support us, and they are new hardware which can be utilized to enhance our approach. In the meantime, and in our research, we also have some idea about the potential hardware design. So we have an intensive conversation with Mona. We meet almost every month, and about our idea using the FPGA to build up a trust execution environment to help accelerate and those AI-based computing, right? And I hope some of our idea could in the end be adopted by industry, because only when they do that will we be able to build up our software stack on top of it to make the technique have a real-world impact. So I think particularly for hardware-driven confidential computing, academia need to work closely with industry. But in the meantime, so we also can provide industry, we also can help industry to explore different directions, particularly in terms of finding out a new application, right? I think the reasons we are part of the Intel's and the TDCOF is because, and we have really good use case, right? Mona, you could see, you can testify that, and we have a really good user and the use case and to apply the technology to healthcare, right? So I think work together we can move this system, we can make it happen.
Okay, thanks. Yeah, so for the industry folks, I'll turn that question around a little bit, right? I know that there are immediate problems that industry tries to solve in the near term, but could you think of anything that you think is more of a long-term problem that you would like to start academia to start exploring right away, for example? Like, yeah, one example that comes to mind is, for example, protection against physical attacks, right? The industry seems to be a little bit lagging given all the constraints about trying to protect against physical attacks and the costs that come with it. But it looks like, yeah, is that something that you think, for example, that academia should really be marching on to solve while industry solves the more near-term problems?
I think Ramya is speaking from personal experience on the replay protection issues. Yeah, no, I think as many of you know, when Intel SGX came out first, we had this memory encryption engine which provided not just confidentiality, integrity, but replay protection guarantees. But it was really expensive if you wanted to scale to large memories, which is where we are today. Right. So, so again, I think, Ramya, it also comes to this balance of practical deployment versus great security, and then can we achieve both? And but can academics come up with a solution that can scale? Of course, yes. I think that remains an solved problem, and depending on what you put in trusted execution environments, if the benefits are, I guess, there's money behind it, then people will be able to attack it. You can put these probes, and it's very, very hard to mount these hardware attacks, right? Especially in the CSPs, those machines are behind protected environments, and it's not that easy to mount the hardware attacks. But should we look into solving that problem? Yes. And I guess there are certain use cases, as I don't know if many of you know, the whole blockchain cryptocurrencies is just, though they are looking at these TEs in a big way. And if you put some high value content in there, I mean, and by the way, we should have, I guess, other area academics should work on. We always assume these TEs are always protected. Once you put something in a TE, it's great, but I think we should also have this, call it the alternate plan. What if it breaks? Do we have other guardrails in place to be able to still get the security guarantees that we believe? So I think that would be one area to go after. I still think this whole disaggregated distributed data center is a big open problem. And there is a little bit a challenge with the access to hardware, because hardware is while industry is developing the hardware, academics can probably work with simulators and FPGA. And both Mohit and Xiaofeng has done some work in that space. But yeah, solving this problem, and someone asked, this whole distributed disaggregated data center and confidential computing problem needs more academic attention, and that's exactly why, by the way, we are funding this center, right? And I think we will be funding going forward in this space, because industry can do, it's the same thing what both Mohit and Xiaofeng said. They can't work in isolation, and we also we need all these great minds working on the problems, so coming up with new solutions. Yeah, I think those are the two areas.
Okay. So, Minsao, do you have, yeah, can you think of like long-term
Let me
problem?
touch several things, right? So I learned a lot from the other panelists, right? So I think there earlier, I think there's Mona actually asked how many people are actually running EDA workload inside the cloud, right? So I can tell you the truth, not a lot. But the biggest barrier is security. So because the EDA used to run in air-gapped environment, so the security, they think the security in a very simplified way. So the security is handled at the boundary of the environment. So you firewall everything, you're done. Within your data center, you don't need to worry about security. Now, when you move into the cloud, that kind of model is not exist anymore. So that is one of the things, is how do you build the confidence from the user? How do you educate them? They are not like you folks work in this area for the last 20 years. How do you let them to understand the security measure there is sufficient? How do you evaluate it? And the other one, as I think Nathaniel actually brought up earlier, is that you have a simplified language so that for the system administrator, whoever that's responsible to set up their cloud environment, to be able to evaluate what is the security measure if this whole system I'm putting together is meeting my requirements, meeting my security requirements. So these are going to lower the barrier for people to adopt all of this new technology, this wonderful technology that we're developing over here, right? So that's one thing. The other thing is, for a software provider like an EDA company like us, we also need to do something like this, because very frequently we get asked by our customer, do you run security scanning for your software? Do you does your software has all these security holes in there? So if we can have some simplified tools or tool chain to actually scan our software and to say, okay, are we implementing all the security measurement there? Are we patching the security vulnerability properly? And also we use all the third-party libraries. So right now we just basically trust the providers and say, okay, we trust them. They provided the next version for the security patch, and we integrated with it, and we feel good about it. We feel good about it. It's usually not a very good answer, right? So it will be nice to have a verification tool that actually you can verify the security measurement is there, right? So that's my input to the
that sounds pretty good, and it ties pretty well to what I would have asked Nathaniel, right? At least in my experience, when I've looked at most trusted execution environment or trusted computing research, a lot of it has gone into architecture work, defining new solutions, right? As opposed to solving very practical deployment challenges that people might face. And clearly, like now we're seeing them emerge because these technologies are gaining momentum. So if you had to, if you had to point to open questions that are hard to solve, which academia could perhaps start looking at, what would be your input?
I have a question for Mona really quick, just to follow up on Min's point. Min just mentioned the burden of doing a kind of like a security audit of your software, right? You have to run like static analysis, stance, dynamic, and running them on really large code bases is full of false positives. And there's just, like he said, lots of opinions and arguments. But if you were to reframe this app into enclaves, the SGX style enclave especially, should we is there a scope for building certifications that kind of are stand-ins for the classic XaaS DAST type of scans, static analysis, dynamic analysis type of scans, but they are relying more on the trusted code-based reduction that you don't actually have to scan a bunch of that other stuff because they are just moving stuff around.
And Xiaofeng wants to answer because I know he's working in this space, but go ahead. Yes, please. Yeah.
And this is exactly what we're doing for our first test. And with our open ecosystem, we call Tap Store. Actually, we're building this code verification certification process into, TE, and also we have blockchain to certify the whole process. And so that's what we're trying to do. Of course, there are a lot of challenges. You cannot move the whole things to the TE because it's, the TCB is too big, too thick. And so what we are doing here is we let people to verify the code, right? But inside the TE, we let untrusted party to build up the proof for the program. For example, we are inside the TE, we check the proof. So that's the preliminary idea. And we can do some simple things now, for example, and we can check SFI. We are moving toward, the information flow policy. right? But I think in general, it's going to be very hard. But and we are trying to just using the ideal proof carrying code and trying to move in toward this direction.
But this is, I think, precisely why we need to focus on TCB minimization is one thing, but decomposing workloads is another. And if we can decompose the workloads and then we can attach certifications through some out of band, transparency log, or you even mentioned blockchain, right? This allows us to certify parts of an application, and then dynamically, right, the certification of the whole emerges as a composition of the parts. So that's the way I kind of look at the problem is, if we can decompose the existing solutions that we have, such that we can have individual certifiers, right? You could have one person run a scan, say, on one portion of an application, and that one portion then gets combined with other portions. And so you can have a security score, for example, for the whole composition, right? Maybe you've done scans on 90% of it. And so you recognize, that you've got a score of 90 or whatever, and maybe that's good enough for you. But being able to speak in a way that is far more dynamic than what we are used to speaking is, I think, the future here.
Yeah, so I think I agree that but I think there is, by the way, that other line of work. So decomposition is one thing, but if you're running that all in the same address space, it doesn't help you. So this fine grain isolation with it, and like for example, Chrome browsers have done that, right? Browsers had these really monolithic code bases, and then they gone site isolation or whatever. So we have to same thing, yeah. So fine, but we do need to put these other fine grain isolation in place. And we have done some work in that space as well, because otherwise today's applications are not built that way. They're monolithic pieces of code, and but not just decomposing and being able to, because otherwise if they impact each other, you still have the problem. But I was also to show while this is great work, we have seen this minimizing TCB is really, really hard, because these EDA tools are complex as it is, right? And then if you go refactor and rework to put in enclaves, I think the challenge is it's non-trivial problem. So I guess the decomposition is one idea, and then and so we'll have to, this is an open area, continue to spend, I guess, research, and just everyone has to remember. And the other thing is not just the bugs. If the software that you put inside the enclave, we all know the software decides to leak secret, enclaves are not going to help you, right? That I think is the big thing people may or may not realize. It's these static analysis of providing certain guarantees about what the software is, or restricting the interfaces is very important. And we are doing that in some of our work. Yeah.
Yeah, I want to affirm one thing you said there. I think the address space problem is a real problem. And it's one of the benefits of the confidential virtual machine technology. Obviously, there's a trade-off in terms of the core TCB. But for confidential virtual machines, we do have the ability to create distinct address spaces, right? Like, everybody does processes today on, whatever operating system you're doing, which is precisely what the kernel does. It manages different processes with different views of memory. And so being able to leverage all of those existing technologies that we have, it is going to pay dividends, because they're already mature, well respected. And what we essentially have to do is we have to identify, for all of the security boundaries that we already have, which is quite a few of them, every time we cross a security boundary, we need to have some metadata in an attestation, right? Because that's the thing that guarantees the boundary between the components. So that's the kind of way that I look at it, is like, let's decompose the parts to make sure they're running in separate address spaces. Let's make sure we attest all the security boundaries, and that gives us something that we can actually evaluate in the real world, which I think gives us a very strong degree of security.
Yeah, so I just want to say, hardware has disaggregation. Now the software need to follow up, right? Need to, just like exactly like Mona and you said, we need to disaggregate it into smaller components so you can measure the security on the component level.
Yeah, but yeah, I think we're almost going to lose people because we're about a minute away. But thank you again very much for your time today and for this fantastic conversation. I come out at least much more educated than I came in. So yeah, thanks again for participating. And I'm sure that people who also watch the recording will find this pretty illuminating. So at this point, I'll hand off to Mohit because I know that there is some official announcement to go around at the end of this conversation.
You mean
Oh,
Saurabh,
sorry
right?
too. Yeah. Saurabh, yeah,
No,
sorry.
no.
I was very worried, but thank you.
Wait, you can do
Sorry.
that too. So yeah, I think the CEDA or HSTTC people, they could not join. I do not see any of them here. They wanted to join, but I think they, for whatever reason, they could not join. So on behalf of them, I would like to say thank you to all the panelists for this exciting panel, like Ramya and like Ming Mei and other attendees. We have got a lot of exciting information from all of you. Definitely, we have gathered a lot of knowledge. We know what to work on in this topic. It's a very, very important topic, and thank you for sharing your insight. So really appreciate your time here. Thanks again to all the panelists. Thanks to our excellent moderators, Ramya and Mengmei. Really appreciate your time and effort in organizing this panel. You did spend a significant amount of effort in finding the best people to attend this panel. So thank you for your effort on composing this panel. And again, really appreciate HSTTC office bearers, particularly Jin, Gangkyu, Shung Hyo. They have spent quite a bit of time in organizing it. And finally, thanks a lot to Laura. Laura has been instrumental force in organizing this effort. And Laura, appreciate your time and effort with this panel. Thank you again. Have a great day.
Thank you very much.
Thank you.
Bye.
Bye.
Thank
Bye.
you.
Bye, buddy.